Good morning, everyone. I'm Jeehoon from the University of Texas at Austin. Today, I'll be presenting our paper titled BIM-Driven Robotic Disassembly for Resource Recovery in End-of-Life Buildings. This paper is co-authored with Professor Christopher Rausch, and I'm sorry I couldn't be there in person, but I'd be glad to answer any questions during the live session or later by email. As many of you know, current construction practices still rely heavily on linear processes, which considers demolition as the final step in a building's life cycle. But this approach leads to two big issues: massive amounts of construction waste and the need to produce even more new materials to meet growing construction demands. This becomes a critical factor to climate change, as you can see on the statistics, where construction and demolition waste accounts for about 30 to 40% of the total solid waste stream. That's around 2.2 billion tons of waste every year. And also, 37% of global energy-related carbon emissions come from producing new construction materials. To mitigate these environmental impacts and move towards a more circular economy, strategies such as reusing, repurposing, or recycling materials from existing buildings and minimizing resource inputs, waste, and emissions in new construction are essential. This approach is often called building as material banks, where we salvage and reuse the materials from buildings of end of life through deconstruction rather than demolition. Despite its potential benefits, the adoption of deconstruction is limited by several key challenges. Buildings are typically designed for long-term functionality, often spanning decades or centuries, with minimal consideration for future material reuse or disassembly. So as a result, applying deconstruction to existing structures poses various structural and technical challenges. For buildings not originally designed to facilitate deconstruction, the process can be time and labor intensive than conventional demolition, and often entails substantial upfront costs. Furthermore, manual labor involved in deconstruction is frequently exposed to safety risks. Still, research shows that with optimized strategies, deconstruction can improve circularity without delaying project timelines or raising costs. So that brings us to our core question of this research. How can we enhance the productivity of deconstruction while overcoming these existing challenges? To answer that, our paper proposes a new approach: planning and executing robotic disassembly of construction entities using BIM. We first generate simulation environments from BIM files that represent the construction entity that's targeted to disassemble, and automatically extracts information of materials that we want to salvage and then plans a deconstruction sequence and the robot path of a manipulator. BIM holds semantic data about a building's component, collected throughout its life cycle. To use this data in a robotic simulation, we need to convert it into a compatible format, a one that keeps the essential attributes of the BIM data. In this study, Autodesk Revit file is converted into a USD file using NVIDIA's Omniverse Revit connector. USD, or OpenUSD, is an open-source 3D ecosystem developed by Pixar that offers a range of advantages for robotic simulation and data representation. The Omniverse Revit connector converts RVT models into USD while preserving essential scene and task information such as geometry and material properties. The resulting USD assets are seamlessly imported into ISARC Sim, the simulation platform used in this study. This allows for integration with other environmental components for a streamlined simulation workflow, such as the robot URDF model and the physical elements such as gravity, collision, and ground plane, which are all activated to complete the simulation setup. Inside ISARC Sim, each building component becomes a prim, short for primitive. These prims retain key data from the BIM file, such as their location, orientation, material type, and bounding box size that bounds the material, the component. With this information, we can filter and isolate specific components, such as materials that are highly reusable, like plastic, and then create a deconstruction plan targeting only the components that we want to salvage. We can access and control the target components using either Python scripts or in our study using OmniGraph, which is ISARC Sim's visual coding tool. Using OmniGraph, we can identify which components we want to recover and automatically generate a robot path to pick and extract them. The left figure shows an example of an OmniGraph node combination that we use in our study, and the image on the right shows an example of the robot that follows this algorithm made by the OmniGraph. So the robot is identifying a target prim, selecting a pickup point, and calculating the inverse kinematics of the robot joint to reach the target points while avoiding collisions with its surrounding environments. To demonstrate how this framework can support robot disassembly planning, a small-scale experiment was conducted using an exposed residential wall assembly unit in the basement of UT Austin. A BIM file that replicates the wall assembly unit was developed by the authors with an approximate level of detail 300, providing detailed information about each component's size, shape, location, and material types. The BIM file was then converted into USD format and imported into ISARC Sim, a robotic simulation platform we used in this experiment. A Franca FR3 robot manipulator was incorporated into the simulation as the robot system and mounted on a static platform to enhance its reachability during the disassembly process. For this experiment, our main goal here was to show that we could use the BIM-derived resource information to detect and extract reusable components. So table 1 gives an example of components from the wall that could be reused, and we used a parsing prompt to identify them and sent the data to the robot controller using OmniGraph. As shown in the video, the robot highlights the component, picks a target point, and calculates its motion path to extract it. This test was limited to just one object, but the same framework can be easily scaled up for multi-object extraction with different material types. To wrap up, this study presented a new framework for automated resource recovery using a robotic system. This presented a new way to facilitate autonomous deconstruction of construction entities, and our method could successfully integrate BIM files with robotic simulation tools, retrieving key material information for deconstruction planning. Our experiment shows how the framework can automatically indicate components with a certain feature and inputs the information for the robot to plan and extract the component. The results show the potential of robotic systems for more productive and safe deconstruction. However, there's still a lot of work ahead to do to deploy this method into real-world environments. First, we need to define what type and formats of construction information should be included in BIM models to optimize the robotic disassembly. Second, adaptive robotic manipulation techniques capable of recognizing and dynamically adjusting disassembly plans are needed. Lastly, the system needs to be more versatile so it can handle on-site constraints and variability. These are our acknowledgements. And that brings me to the end. Thank you for listening, and I'm happy to answer any questions or comments during the live session if possible, or feel free to reach out to me by email using the address on this slide. Thank you.